Have you ever tried to solve a problem quickly, but somehow it just didn't work out? We are thinking that if you could just guess the solution, the problem would become so much easier. Of course, this is a silly thought. How could you solve something by simply guessing? However, is it really that silly? Actually, no. And you can achieve quite a lot with some good old guessing. To see this, let us start with a small story. Imagine that you and your casual bank robber friends have stolen a necklace made up of n different gems. Now, you would like to cut the necklace into k smaller pieces so that each of you gets exactly one continuous piece. The problem is that the gems of the necklace are not the same, meaning that they have different values. So some pieces might be more valuable than others. Here, the value of a single necklace is simply the sum of the values of its gems. Of course, you and your friends are all honest guys, aside from occasionally robbing a bank. But what is robbing a bank compared to founding one? Anyway, you would like to divide the necklace fairly so that none of you gets too angry. One way to define fairness is to ensure that the person who gets the least valuable piece is as well off as possible. In other words, we want to partition the necklace in a way that maximizes the value of the least valuable piece. This idea is known as egalitarian welfare. For example, here, the least valuable necklace has a value of 125, meaning that the value of the entire partition is 125. However, if we cut it in this way instead, the minimum jumps to 175, so the second partition is clearly a fairer one. Now, this raises the question, how can we actually compute the partition that is the fairest? To figure that out, it helps to abstract the problem a little so that we can feed it into a program. Instead of thinking about a physical necklace, we will assume that we are given an array A of n integers, where each number lies in the range from 1 to n to the power of 6. These numbers represent the value of the individual gems, and this n to the 6 will play an important role later. Further, we are getting an integer k as an input, and our goal is to partition the array A into k continuous pieces such that the smallest sum among all of these pieces is as large as possible. Formally, we define the value of a partition as the smallest value of some piece. The optimal value is now the maximum possible value over all valid partitions, where valid just means that the array is split into k connected continuous pieces. That's just a reformulation of our original necklace problem, where the gems have been replaced with integers. But before we continue, I would like to give you a moment to pause the video and try solving it yourself. Your goal should be to design an algorithm that runs in time O of n log n, where n is the length of the input array A. Assume that you are trying to divide the necklace when suddenly one of your friends has a divine inspiration. He says that he doesn't know how to divide the necklace, but he is sure that there is a partition whose value is at least 125. Now the question is, how can we check if the divine inspiration of our friend is actually correct? For this, let's reformulate the problem. Your task is now to cut the necklace into k smaller pieces such that each piece has a value of at least 125. The easiest way to achieve this is to start at one end of the necklace and start adding gems one by one, always keeping track of the total value. Once the value of the current piece reaches at least 125, we make a cut. But why exactly at this position? First, we cannot cut any earlier because otherwise the first piece wouldn't be valuable enough. And second, by cutting it as early as possible, we leave as many gems as possible for the remaining parts, giving us a better chance of succeeding overall. So, if it's possible to cut the necklace into k parts where each piece has a value of at least 125, then this greedy method is able to find such a partition. Once we have made the first cut, we are left with a smaller necklace, and now we have to divide it into k-1 pieces. So we simply repeat the whole process. We keep adding gems until the total value is at least 125 and make a cut. We continue doing this until we have made k-1 cuts. The last piece, which is the remaining necklace, goes to the last person. However, we need to check if the total value of the last piece is also at least 125 to ensure that the last person also gets enough. That way, we split the necklace into k parts, all having a value of at least 125. This also works if we replace 125 with another constant x. But there are two problems with this approach. The first one is, what the heck? This solution isn't fair at all. Somehow, the guy who just made the guess ends up with the biggest piece. Maybe he had some devilish inspiration after all. Although his claim that the optimum is at least 125 was actually correct. So, what went wrong? The issue is that his guess was just way too low. I wonder why. Still, there's another kind of problem that might occur. Let's say that our friend makes a new guess. This time, he's far too generous and claims that the optimum is at least 300. Now, we apply the same strategy as before and start adding gems to the current piece until we reach a value of at least 300. We make a cut and do this for the second piece as well. However, while processing the third piece, we realize that we have not enough gems anymore, meaning that we cannot fulfill our friend's request. This happened because there's no valid way to cut the necklace into 4 pieces that all have a value of at least 300. Thus, we can simply tell our friend that his request is impossible. To summarize, first, the process that we just described returns bad results if our friend guesses a value that is far less than the optimum. Second, the process returns that no solution is possible if our friend guesses something higher than the optimum. So the whole process only works if we already know the value of the optimal solution. But how can we find such a value without divine intervention? This is where we will actually use guessing. Before that, let's first translate this process into code. The following is some pseudocode that closely resembles Python. We start by initializing a few variables. Cuts is the list that will hold the k different pieces of our final partition. Further, P is the list of all gems that represent the current piece that we are processing, and value is the value of that piece. We use this notation here to represent the length of a list. The algorithm iterates over all gems from left to right, adding each gem to the current piece. Whenever the value of the current piece becomes greater than or equal to x, we make a cut. That means that we add the current piece to our cut list and we set both the piece and its value so that we can begin building the next one. We repeat this process until we have processed all gems. This condition here ensures that we create at most k-1 many cuts, which is important because the last person should just get whatever gems are left. At the end, we check whether we have successfully cut the necklace into k pieces and whether the final piece, that one that goes to the last person, has a value of at least x. If both conditions are satisfied, we return our solution. Otherwise, we return none to indicate that no valid partition exists for the given x. This greedy algorithm runs in time O of n, since we only loop through the array once. Further, the function gives us the following guarantee. If x is at least the optimum value, then it outputs a partition whose value is at least x. If x is larger than the optimum value, then it returns that there is no valid partition whose value is at least x. With this algorithm, we check if a guess of our friends makes any sense. However, the function only returns an optimum cut if our friend's guess was already optimal. But how can we make such a guess without solving the problem in the first place? For this, we need one more observation. Even though we don't know the optimum value, we can try to find reasonable lower and upper bounds for it. For that, we use the fact that the gem values all lie between 1 and n to the 6. If we have more people than gems, then at least one of our friends ends up with nothing. So in that case, the optimum value has to be 0. On the other hand, if there's only one person, we can just hand over the entire necklace. And since each gem has a value of at most n to the 6 and there are n different gems, the total value of the necklace is at most n times n to the 6, which gives us an upper bound of n to the 7. This means that the solution is somewhere in this interval. We only have to find it. Still, the solution can be any value within the interval. So, what should we do if we don't have any clue? Why not just take the middle and hope for the best? Luckily, we have our check function from before, which allows us to see if our guess makes any sense. If the algorithm finds a partition, then the true optimum value is at least as large as our guess. That means that the optimum lies in the right half of the interval. If the algorithm says that no valid partition is possible, then the optimum value has to be strictly smaller than the middle, so it lies in the left half. Now, we simply repeat the whole process with the rest. We choose the middle of the remaining half and use our check function on it. Again, the algorithm tells us in which half the optimum value is. We repeat this process to make the search interval smaller and smaller. Since we are actually working with natural numbers, at some point we enter a situation that our search interval only consists of a single point. This single point must be the true optimum value, and running check on it will return the optimal partition of the necklace. This method, which you probably know as binary search, only needs to call our check function about log of n to the 7 many times, since this is the size of our initial search interval. Using logarithm laws, we can rewrite this into 7 times log n. So the whole algorithm looks like this. We begin by defining the left and right boundaries of our search region. The right boundary is just the sum of all gem values. Further, we use the variable ans to store the best cut we have found so far, and the variable opt for the value of that cut. We perform our search as long as our search interval is non-empty, meaning that the left boundary is at most the right boundary. In each round, we compute the middle of our search interval and call our check function on it. If check returns a valid cut, then we know that the optimum value is at least as large as the middle. So we shift the left boundary to one more than mid. This way, we only consider larger values from here on now. And since we just found a valid cut with value at least mid, we can store it as our current best guess. If check returns that no valid cut is possible, then we know that all values greater than or equal to the middle will also fail. So we move the right boundary to one less than the middle to exclude the entire upper region. We repeat this process until the search interval becomes empty, and when that happens, we have found the largest possible value for which a valid cut exists. We return the corresponding cut as our final result. Since each call to our check function takes time O of n, and we perform at most logarithmic many such calls, the total running time is in O of n log n. I also want to point out that the algorithm itself does not rely on any form of randomness. However, there's another way to solve the same problem by using dynamic programming. For this, we have to create a 2D dp table where the entry jm is the optimum value of splitting the first m entries of the array into j parts. The final solution can be found by computing the entry kn, which is why our dp table consists of k times n many entries. Each entry can be computed in time O of n, which means that the total running time is in O of k times n square, meaning that we can greatly outperform this dynamic programming approach by simply guessing the solution and checking it later. Sometimes simply guessing is the smartest way to solve it.